Before Schrödinger's equation existed, physics was in trouble. Classical physics, the physics of Newton and Maxwell, worked beautifully for planets, pendulums, and electricity. But when scientists looked inside the atom, everything fell apart. Electrons did not behave like tiny planets orbiting a nucleus. Atoms emitted light at specific frequencies only, not continuously. Classical equations predicted atoms should collapse, yet they were stable. This was not a small problem. It was a crisis of reality itself. Physicists realized that the laws governing the everyday world were incomplete. Something deeper was operating at the microscopic level. The birth of a radical idea. In 1924, Louis de Broglie proposed something shocking. If light can behave like a particle, perhaps particles can behave like waves. This idea suggested that matter itself has a wave nature. Erwin Schrödinger took this idea seriously. He asked a bold question. If electrons behave like waves, can we write a wave equation for matter? That question led to one of the most important equations ever written. In 1926, Schrödinger published an equation that described how a quantum system evolves over time. This equation did not tell us where a particle is, what path it follows. Instead, it told us something far more subtle. It tells us how possibilities evolve. At the heart of Schrödinger's equation is a mathematical object called the wave function, usually written as psi. What is the wave function? The wave function is not a physical wave like a water wave. It does not represent a vibrating electron or a smeared-out particle. Instead, it encodes information. Specifically, the wave function contains all possible outcomes of a quantum system. When we take the square of its magnitude, we obtain probability. That means Schrödinger's equation governs the probability itself. That is a radical departure from classical physics, a profound shift. Classical physics said, if you know the present exactly, you can predict the future exactly. Schrödinger's equation says, if you know the present exactly, you can predict probabilities. Reality at its most fundamental level is not deterministic in outcome, only in evolution. Schrödinger's equation plays a role in quantum mechanics similar to Newton's laws in classical mechanics. But there is a crucial difference. Newton's laws describe motion of objects, deterministic trajectories, clear cause and effect. Schrödinger's equation describes evolution of wave functions, deterministic mathematics, probabilistic reality. This leads to a deep paradox. The equation evolves perfectly and deterministically, yet the world appears random. Time evolution, the heart of the equation. One of the most important features of Schrödinger's equation is that time enters explicitly. This means the wave function changes smoothly over time. Possibilities flow, interfere, and reshape. Quantum systems do not jump randomly. They evolve continuously, until a measurement is made. This idea deeply disturbed Schrödinger himself. He believed nature should be continuous, not probabilistic, yet his own equation forced probability into the heart of physics. Schrödinger's regret. Schrödinger famously disliked the interpretation of his own work. He once wrote, "I don't like it, and I'm sorry I ever had anything to do with it." Despite this, the equation worked perfectly. It explained atomic structure, chemical bonds, spectral lines. Reality had chosen mathematics over intuition. One of the simplest and most revealing applications of Schrödinger's equation is the particle in a box. Imagine an electron trapped between two perfectly rigid walls. It cannot escape, it cannot exist outside. Classically, this particle could have any energy. Quantum mechanically, Schrödinger's equation says only certain energies are allowed. Standing waves, not orbits. The solutions to Schrödinger's equation in this case are standing waves. Just like a guitar string, only specific wavelengths fit, only specific frequencies resonate. Similarly, only specific wave functions fit inside the box. Each corresponds to a discrete energy level. This is quantization, and it is not imposed by hand. Quantization emerges naturally from the equation itself. A deep insight. Nature does not forbid intermediate energies by force. Instead, they simply cannot exist mathematically. This reveals something profound. Reality is constrained by structure, not rules. Mathematics shapes existence. Reference: Griffith's Introduction to Quantum Mechanics, Chapter 2. Before Schrödinger's equation, classical physics predicted a disaster. Electrons orbiting a nucleus should radiate energy, spiral inward, destroy the atom. Yet atoms are stable. Schrödinger's equation explains why. Atomic orbitals are not orbits. Electrons do not travel in neat paths. Instead, they exist as probability clouds. These clouds are stable solutions to the equation. The lowest energy wave function, the ground state, cannot lose energy. There is nowhere lower to go. This is not a force. This is geometry of possibility. Why chemistry exists. Because of Schrödinger's equation, atoms have structure, molecules form, chemistry becomes possible, life emerges. Every chemical bond is a solution to Schrödinger's equation. Reference: Dirac, The Principles of Quantum Mechanics. Atkins and Friedman, Molecular Quantum Mechanics. One of the most unsettling consequences of Schrödinger's equation is superposition. The wave function can be here and there, this energy and that energy, simultaneously. This is not ignorance. This is reality as described by the equation. Schrödinger's cat was a protest. Schrödinger introduced his famous cat not to support quantum weirdness, but to criticize it. He wanted to show how absurd superposition becomes at large scales. Yet experiments have consistently confirmed superposition is real. Interference patterns prove it. The discomfort is not experimental, it is philosophical. Here we encounter a crucial fact. Schrödinger's equation never collapses the wave function. Collapse is not in the mathematics. The equation describes smooth, continuous, deterministic evolution, but measurement gives one outcome, one reality. This is the measurement problem. What the equation does not explain. Schrödinger's equation does not explain why one outcome occurs, when collapse happens, whether collapse is real at all. This gap is not solved, not in 100 years. Different interpretations attempt to answer it. Copenhagen interpretation, many worlds, objective collapse theories. All agree on the equation, none agree on reality. Here lies one of the deepest insights in physics. Schrödinger's equation is fully deterministic. If you know the initial wave function, the potential, you can calculate the future wave function exactly. Yet outcomes are probabilistic. Measurement introduces irreducible randomness. This creates a strange hybrid, deterministic evolution of indeterminate events. This is unlike anything in classical science. Einstein's objection. Einstein famously objected, "God does not play dice." But Schrödinger's equation does not play dice. Reality does. The equation only involves possibilities. Reference: Einstein, Podolsky, and Rosen, 1935. A fundamental unanswered question. Is the wave function a real physical object or just information? Two camps exist. Ontic view. Wave function is real. Reality is fundamentally non-local. Epistemic view. Wave function encodes knowledge. Reality exists independently. Experiments increasingly favor ontic interpretations, but the debate remains open. This is not philosophy detached from science. It shapes how we interpret experiments. Schrödinger's equation underlines transistors, lasers, MRI scanners, quantum dots, semiconductor physics, quantum computing. Every silicon chip solves Schrödinger's equation billions of times per second. Modern civilization runs on probability waves. At its core, Schrödinger's equation has two essential ingredients: time evolution and energy balance. In its time-dependent form, the equation relates the rate of change of the wave function to the total energy of the system. What matters conceptually is not the symbols, but the structure. Change in time is governed by energy. This mirrors classical physics. Energy generates motion.
Hamiltonian generates evolution. But here, energy does not move particles, it moves possibilities. Why the equation is linear? One of the most important features of Schrödinger's equation is linearity. This means if psi1 and psi2 are solutions, then psi1 plus psi2 is also a solution. This is the mathematical origin of superposition, interference, and quantum parallelism. If the equation were nonlinear, superposition would fail. Quantum mechanics would collapse into classicality. Reality's strangeness is not optional, it is enforced by linearity. Reference: Modern Quantum Mechanics, Chapter 2. A critical and often misunderstood fact. Measurement does not appear anywhere in Schrödinger's equation. The equation describes isolated systems, perfect, uninterrupted evolution. But real experiments involve observers, apparatus, environment. The moment measurement enters, the equation stops speaking. The measurement problem restated precisely. There are three statements that cannot all be true. The wave function evolves according to Schrödinger's equation, measurements have definite outcomes, and the wave function is complete. Quantum mechanics forces us to abandon at least one. This is not philosophical confusion, it is a logical impossibility. Reference: Speakable and unspeakable in quantum mechanics. One modern attempt to bridge the gap is decoherence. Decoherence explains why interference disappears, why macroscopic objects behave classically, why superpositions become unobservable. It occurs because quantum systems interact with their environment. Phase information is lost. Decoherence explains why we don't see superpositions, explains emergence of classical behavior. But decoherence does not select a single outcome, cause collapse, or solve the measurement problem. It hides the problem, it does not remove it. One interpretation makes a radical move. What if Schrödinger's equation is never violated? In the many worlds interpretation, the wave function never collapses. All outcomes occur. Reality continuously branches. Nothing mystical is added, nothing is removed. Only the equation is trusted. Physicists consider it seriously because it removes collapse postulates, it preserves determinism, it respects the equation fully. Its cost? An enormous branching reality. Its benefit? Mathematical honesty. Reference: The Emergent Multiverse. Despite its success, Schrödinger's equation is not the deepest law. It fails in three major regimes. Relativity. Schrödinger's equation assumes absolute time, violates relativistic symmetry. This led to the Klein-Gordon equation and the Dirac equation. Relativity demands space and time be treated equally. 2. Particle creation and destruction. Schrödinger's equation assumes fixed number of particles, but reality allows particle creation and annihilation. This requires quantum field theory. 3. Gravity. The equation does not include curved spacetime, gravitational interaction at quantum scale. This remains unsolved. Modern physics replaces Schrödinger's equation with something deeper. Fields, not particles, are fundamental. In quantum field theory, fields exist everywhere. Particles are excitations. Probability still rules. Schrödinger's equation survives only as a low-energy, non-relativistic approximation, yet it remains one of the most successful approximations in history. After everything, the equation leaves us with unsettling lessons. Reality is not made of objects, it is made of relations and possibilities. Determinism governs evolution, probability governs experience. The universe does not compute outcomes, it evolves structure. Schrödinger's equation raises a final question science has not answered. Is reality evolving, or is information evolving? If the wave function is real, reality itself is non-local. Space is not fundamental. If the wave function is informational, reality exists beneath probability. Quantum mechanics is incomplete. Both possibilities are profound. Neither is resolved. One detail almost everyone overlooks: Schrödinger's equation requires complex numbers. This is not mathematical decoration. If the equation were purely real, quantum mechanics would fail. The imaginary unit, I, ensures oscillatory behavior, reversible time evolution, conservation of probability. Without it, probabilities would grow or decay uncontrollably. Reality would not be stable. Complex numbers encode phase, and phase is what allows interference, superposition, coherence. Quantum reality is not built from quantities alone, but from relationships. Schrödinger's equation enforces a principle called unitarity. Unitarity means total probability is always conserved. Information is never destroyed within the equation. Even when outcomes appear random, the wave function remains perfectly ordered. Evolution is reversible in principle. This is why quantum mechanics is often described as perfectly lawful beneath apparent chaos. A deep consequence: if Schrödinger's equation is exact, information loss is impossible. True randomness does not exist at the fundamental level. This clashes sharply with measurement collapse, black hole evaporation, thermodynamic irreversibility. This tension is still unresolved. When multiple particles are described together, Schrödinger's equation produces entanglement. This means the wave function cannot be factored. Individual particles lose independent existence. The equation no longer describes objects, it describes relationships. Why entanglement is not interaction? After entanglement, measuring one particle changes predictions for another. No signal travels, no force acts. What changes is the global wave function. Reality updates holistically, not locally. Einstein called this spooky action at a distance, but it is simply the equation doing its job. Schrödinger's equation allows entanglement across space. This suggests spatial separation is not fundamental. The wave function lives in configuration space, not physical space. For many particle systems, the wave function does not exist in 3D space. It exists in a high-dimensional abstract space. This raises a disturbing possibility. Space may be emergent, not fundamental. Reference: Albert, Quantum Mechanics and Experience. In Schrödinger's equation, time is external. It flows uniformly. It is not an operator. This is fundamentally different from position, momentum, energy. Quantum mechanics assumes time, it does not explain it. A quiet crisis. When combined with general relativity, time becomes dynamic. Geometry evolves. Schrödinger's equation breaks. This leads to the problem of time in quantum gravity. The equation requires time, but time itself may not exist fundamentally. Reference: Rovelli, Quantum Gravity. The everyday world appears definite, continuous, local, but Schrödinger's equation never produces definiteness. Classical reality emerges only when phases decohere. Interference becomes inaccessible. Observers lose information. Classical physics is not wrong, it is incomplete. Certainty is an illusion born of complexity. Despite popular myths, Schrödinger's equation says nothing about conscious observers, awareness, mind-induced collapse. Measurement problems arise from physical interaction, not perception. Consciousness is not required, confusion is. Yet Schrödinger himself speculated deeply about mind and unity outside the equation. The mathematics remains indifferent. At its deepest level, Schrödinger's equation may not be a law of motion. It may be a rule of consistency, a constraint on allowable realities, a filter on what can exist. It does not command reality, it permits it. A subtle but profound reinterpretation used by modern theorists. Schrödinger's equation does not drive reality, it constrains it. In classical mechanics, laws cause motion. In quantum mechanics, the equation restricts which histories are allowed. Reality does not obey the equation moment by moment. Rather, only those histories consistent with it can exist. This view aligns with path integral formulation, principle-based physics like relativity. Nature selects from allowed structures, not from causes. Richard Feynman reformulated quantum mechanics without directly using Schrödinger's equation. Instead of one evolving wave function, he proposed all possible paths contribute. Each path is weighted by a phase. When summed, classical paths emerge, quantum interference appears. Why this matters? The Schrödinger equation and the path integral are mathematically equivalent, but conceptually, Schrödinger equals local evolution, path integral equals global consistency. This suggests that reality is not built step by step, it is selected all at once. This is deeply non-classical. Reference: Feynman, Space-Time Approach to Non-Relativistic Quantum Mechanics, 1948. Schrödinger's equation preserves correlations without preserving classical causation. In quantum mechanics, effects are not always traceable to causes. Correlations exist without signals. The equation allows strong correlations without causal mechanisms. This does not violate relativity. It violates classical intuition. Quantum mechanics replaces causation with consistency. Reference: Wood in Speckens, The Lesson of Causal Discovery Algorithms for Quantum Correlations. In classical probability, probability equals lack of knowledge. In quantum mechanics, probability is fundamental. Even with complete knowledge of the wave function, outcomes remain probabilistic. Schrödinger's equation does not evolve ignorance, it evolves objective uncertainty. This is a radical shift in the meaning of probability. Why this cannot be classical? Bell's theorem proves that no local hidden variables can reproduce quantum predictions. Thus, quantum probability is not reducible to classical randomness. Schrödinger's equation is time reversal symmetric. If time were reversed, the equation still holds. Yet experience is not symmetric. We remember the past, not the future. This asymmetry does not come from the equation. It comes from initial conditions, entropy, environment. The equation does not explain time's arrow, it tolerates it. Reference: Price, Time's Arrow and Archimedes' Point. A growing view in modern physics, the quantum state is an information structure constrained by physical law. This does not mean subjective, it means relational, context-dependent, non-absolute. The Schrödinger equation governs how information structures transform, not how objects move. This changes the question. Instead of asking, what is the particle doing, we ask, how is information reorganizing? This aligns with quantum information theory, black hole physics, holography. Quantum mechanics has been extended, reinterpreted, embedded into deeper theories, yet the Schrödinger equation always reappears as a limit. Why? Because it encodes linearity, probability conservation, continuous symmetry. Any deeper theory must reproduce these features. It is not fundamental, but it is unavoidable.
Some modern approaches suggest Schrödinger's equation is emergent. It arises from deeper statistical or geometric principles. Proposals include entropic dynamics, information geometry, quantum as emergent from classical ensembles. If true, quantum mechanics is not fundamental, it is thermodynamic in origin. This remains speculative but mathematically consistent. Consider this carefully. If Schrödinger's equation governs evolution of information, not evolution of matter, then matter is derivative, reality is relational, objects are secondary. What exists fundamentally may not be things, but constraints on possibility. A striking idea in modern physics, space may be built from entanglement. In Schrödinger's equation for many body systems, entanglement patterns determine correlations. Geometry does not explicitly appear. Yet, in gravity and relativity, geometry is the physics. This leads to a proposal. Spatial distance corresponds to entanglement strength. Highly entangled systems are close. Weakly entangled systems are far. Thus, space may emerge from quantum structure. Why Schrödinger's equation is central here. The equation governs how entanglement forms, how it spreads, how it reorganizes. Without Schrödinger evolution, no controlled entanglement, no emergent geometry. Space may be a secondary concept born from wave function structure. Reference: Van Ramsdonk,
Building Up Spacetime with Quantum Entanglement, 2010. In certain limits, the wave function's entanglement entropy behaves like geometric area. This mirrors black hole entropy, the holographic principle. Here, Schrödinger's equation does not move particles, it sculpts geometry indirectly. The equation governs the architecture of reality, not its contents. Reference: Ryu and Takanagi, Holographic Entanglement Entropy, 2006. Black holes present a challenge. Schrödinger's equation enforces unitarity. Black hole evaporation appears to destroy information. This contradiction is known as the black hole information paradox. If Schrödinger's equation is correct, information must escape or remain encoded somehow. Modern results increasingly suggest unitarity survives. Schrödinger evolution is never violated. This elevates the equation from a model to a consistency requirement. Schrödinger evolution is continuous, differentiable, smooth in time. Nature seems to prefer smooth evolution of probability even when outcomes are discrete. This smoothness is not demanded experimentally, it is demanded mathematically. Discontinuous evolution would break probability conservation, destroy coherence, violate symmetry. Continuity is not observed, it is required. The wave function lives in a Hilbert space, not physical space. This is essential because Hilbert space supports inner products, allows probability interpretation, enforces orthogonality of states. Hilbert space is not a convenience, it is the minimal structure required for consistent probability evolution. Reality, at its deepest description, may live in abstract spaces, not physical ones. In Schrödinger's formulation, observables are operators, states come first. This is opposite to classical thinking. Classically, objects have properties. Quantum mechanically, properties arise from state-operator interaction. Thus, there are no properties without context. The equation evolves states, not properties. Schrödinger's equation never refers to particles. It evolves states, amplitudes, correlations. Particles emerge only when states localize, measurements constrain possibilities. Particles are events, not entities. The equation knows nothing of objects, only structure. Because the wave function includes unrealized possibilities, Schrödinger's equation evolves outcomes that never occur. These unrealized branches still affect interference. Thus, what could have happened influences what does. This violates classical realism. Quantum mechanics cares about counterfactual structure, not just facts. Reference: Perez, Quantum Theory, Concepts and Methods. Quantum propositions do not obey classical logic. Because superposition violates exclusivity, measurement context matters. This leads to quantum logic, non-Boolean truth structures. Schrödinger's equation evolves states in a space where truth is not binary. If space emerges from entanglement, time is external and unexplained, probability is fundamental, objects are secondary, then Schrödinger's equation may not describe things at all. It may describe constraints on consistency, allowed patterns of correlation, the grammar of reality. Not what exists, but what is allowed to exist together. A key question Schrödinger's equation does not ask, but quietly answers: why do many observers agree on the same reality? If the wave function contains superpositions, why don't we see them? Redundant information, not collapse. Quantum Darwinism proposes the environment monitors quantum systems. Certain states leave many copies of themselves. These states become objective. Schrödinger's equation governs system-to-environment interaction, proliferation of information, stability of certain outcomes. Classical reality is not selected by observers, it is selected by redundancy. What survives is what can be copied. Reference: Zurich, Quantum Darwinism, 2009. Objectivity arises when many fragments of the environment carry the same information, independently accessible. Schrödinger's evolution ensures that some states spread information efficiently, others remain fragile and invisible. Thus, reality is what multiple observers can agree upon without disturbing the system. Reality becomes a public phenomenon, not a fundamental one. Classical science assumed the whole is explained by parts. Quantum mechanics reverses this. Because entangled systems have no independent parts, properties belong to the whole. Schrödinger's equation evolves global states, not separable components. Reductionism fails quietly, mathematically. The universe is not built bottom-up, but coherently. Reference: Howard, Holism, Separability, and the Metaphysical Implications of the Bell Experiments. Schrödinger's equation itself may be a stable emergent pattern, not a primitive rule. Just as thermodynamic laws emerge from statistics, classical mechanics emerges from quantum mechanics, quantum dynamics may emerge from information constraints, symmetry, consistency requirements. This suggests laws are habits of nature, not commands. Schrödinger's equation respects deep symmetries: time translation, spatial translation, phase invariance. By Noether's theorem, symmetry to conservation. Energy conservation arises not from force, but from temporal symmetry. The equation encodes symmetry, not mechanism. The equation does not assign causes, effects. It assigns amplitudes, correlations. Causality emerges only when decoherence suppresses interference. Classical approximations apply. At the quantum level, correlation replaces causation. This is not philosophical, it is structural. Despite radical implications, Schrödinger's equation is exceptionally stable, extremely constrained, resistant to modification. Attempts to alter it slightly often lead to faster-than-light signaling, probability violation, logical inconsistency. This suggests the equation sits at a consistency fixed point. Reality may have very little freedom. The same equation governs electrons, atoms, molecules, superconductors, Bose-Einstein condensates. Scale does not break it. Only approximation hides it. Universality hints this is not a model, it is a framework. Consider the following shift. Schrödinger's equation may not describe motion. It may describe grammar. States are sentences. Operators are transformations. Evolution is syntax. Reality is not computed, it is well formed. Only grammatically consistent realities exist. Even with perfect knowledge of the wave function, outcomes are unpredictable. Only distributions are knowable. This is not technological ignorance, it is ontological limitation. The universe permits exact laws, inexact events. Schrödinger's equation enforces this boundary. A question Schrödinger himself worried about but never resolved: why does mathematics describe nature so precisely? Schrödinger's equation is not empirical in form. It is mathematically inevitable once certain assumptions are accepted: linearity, continuity, probability conservation, symmetry under time translation. Once these are granted, the structure is almost forced. This suggests physics may not discover laws, it uncovers necessities. The universe does not choose Schrödinger's equation. Any consistent universe may be unable to avoid it. Reference: Wigner, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. If Schrödinger's equation were slightly altered, linearity broken, phase disturbed, unitarity lost, then superluminal signaling appears, probability fails, logical contradiction emerges. This severely limits alternatives. Thus, quantum mechanics is not strange, it is constrained. Reality may look odd because the alternatives are impossible. In modern theoretical language, Schrödinger's equation behaves like a fixed point. Perturb it. Inconsistency grows. Physical meaning collapses. Stable theories flow back toward it. This is why nonlinear quantum theories fail. Hidden variable fixes struggle. Modifications introduce paradoxes. The equation is not delicate, it is rigid. Classical physics explains laws via mechanisms, models, intuition. Schrödinger's equation admits none of these. It does not explain why probabilities exist. It only ensures they are consistent. At this level, explanation is replaced by constraint. There may be nothing beneath. Reference: Lang, the laws of nature. The wave function does not represent events, it represents a space of possibilities. Schrödinger evolution reshapes that space, stretching, rotating, interfering. Events are merely selections from that space. Thus, possibility is primary, actuality is secondary. This reverses everyday metaphysics. A subtle but critical point. Schrödinger's equation contains no events. There is no collapse, no occurrence, no moment of happening. It describes timeless evolution. Events appear only when systems interact irreversibly. Information is lost to the environment. The equation itself is eventless. Some suggest the universe computes its future, but Schrödinger's equation does not compute, it constrains. No steps, no memory, no algorithm. Reality does not calculate outcomes, it permits them. This undermines digital universe metaphors. If reality were a simulation, the equation would be a rule inside it, but the equation defines consistency, not implementation. Any simulation capable of quantum behavior must itself obey similar constraints. Simulation does not explain the equation, it presupposes it. Schrödinger's equation has no purpose, no optimization, no direction, yet it generates stability, complexity, life. This is order without intention. Structure emerges not because it is favored, but because it is allowed. No drama exists in the equation. No particles collide, no waves crash, no choices are made. Only smooth evolution of amplitudes. The violence of the world, explosions, stars, decay, is emergent. Fundamentally, reality is calm. At this depth, Schrödinger's equation appears not as a physical law, a model, a description, but as a condition for coherence. A universe that violates it may not be describable, observable, or even thinkable. The equation may not explain reality, it may be what makes reality possible at all.
Consider this carefully. If Schrödinger's equation is a constraint on consistency, then a deeper question emerges. Can absolute nothingness be consistent? A state with no structure, no relations, no possibility cannot evolve, cannot be described, cannot even be assigned probability. In this sense, nothing is unstable. The moment consistency exists, structure must appear. Quantum mechanics does not explain why something exists. It suggests why nothing may not be allowed. Once probability exists, it must be conserved. It must evolve smoothly. It must respect symmetry. These demands alone lead toward Schrödinger-like dynamics. Structure is not chosen, it is forced. Reality does not emerge because it is interesting, but because alternatives violate consistency. Despite appearances, turbulence, noise, random decay, at the deepest level, evolution is smooth. Phases rotate, amplitudes flow. Chaos is emergent from sensitivity, complexity, decoherence, but the underlying equation is quiet and stable. Disorder lives on top of order, not beneath it. Language assumes objects, events, causes. Schrödinger's equation uses none of these. It speaks in states, operators, transformations. When we ask, what is really happening? The equation offers no answer because the question presupposes classical meaning. At this level, meaning is emergent, not fundamental. Wave mechanics, matrix mechanics, path integrals, quantum information, all are mathematically equivalent. No formulation is privileged. This suggests there is no true picture of reality, only consistent ones. Reality is not visualizable, only formalizable. Human intuition evolved for mid-scale objects, slow speeds, local causes. Schrödinger's equation violates all three. The failure is not in physics, it is in biology. The universe is not obliged to be intuitive. At this depth, every why becomes a request for deeper consistency, not deeper mechanism. Eventually, no further reduction is possible, only acceptance of constraint remains. This is not mysticism, it is the boundary of explanation. Schrödinger's equation may not sit at the bottom. It may mark the lowest level at which description is possible, the edge of intelligibility. Below it, concepts dissolve, mathematics may fail, description may be meaningless. The equation is not the ground of reality, but the shoreline of understanding. No deeper narrative appears, no hidden mechanism emerges, no final picture resolves, only structure, constraint, consistency. The universe does not explain itself, it simply remains consistent. At this depth, reality has no center, no purpose, no final layer, only what is allowed, what is forbidden, what remains stable. Schrödinger's equation stands not as an answer, but as a condition for questions to exist at all. After peeling away particles, trajectories, causes, even space-time itself, what remains is not an object, but a rule, how possibilities relate to one another. Schrödinger's equation does not tell us what exists, it tells us what is allowed to coexist consistently. At this depth, reality is not built from things, it is built from constraints, from relationships that cannot contradict themselves. The universe is not a collection of objects moving in time, it is a self-consistent unfolding of possibilities. Schrödinger's equation is simply the most economical way we know to express that unfolding. Not why it happens, not what it means, only how it must proceed if it proceeds at all. Schrödinger once hoped his equation would restore continuity and intuition to physics. Instead, it quietly removed certainty, objects, and even the idea of a single unfolding reality. Yet something remarkable happened. Despite all the uncertainty, atoms held together, chemistry emerged, stars ignited, life appeared, minds asked questions. All of this arose not from certainty, but from structured probability. Perhaps that is the final lesson hidden in the equation. Reality does not need to be definite to be stable. It does not need to be certain to be real. It only needs to be consistent. And Schrödinger's equation, calm, mathematical, indifferent, is the rule that keeps that consistency intact. Not as an answer, not as a final truth, but as a quiet guide to how reality evolves.